This one is about our experiment number 3, lab 3, which is a design of a common emitter amplifier. And let me tell you what these specifications are. So what we have is a RC coupled common emitter amplifier, a well-known RC coupled common emitter amplifier, which is over here. And so this is the amplifier that you have to design. The specifications are given. Gain greater than 100, small signal voltage gain greater than 100, input resistance greater than or equal to 0.5K, output resistance less than 2K, maximum voltage swing peak to peak, which is 1.6 volt with harmonic distortion less than 5%. Load resistance is given is 2K, and supply voltage is 12 volt. And the transistor is the one that you've been working with, BC547, the same transistor that you used in experiment number 1. Okay, so these are the specs which are given, and for these specs you have to design this particular amplifier, and you have to breadboard it, and you have to measure the performance of this amplifier and show that your design matches with what your expectations are. All right, so let me start with the design is not as simple as it may seem, and this is not the complete specifications. I'll add a little bit of complexity a little later on. Okay, right now let's just look at this particular specs here, and let's look at how one may do the design. And we have all these design equations that you're well familiar with from your last course: expressions for voltage gain, expressions for input resistance. These are all input resistance, R pi parallel RB. R pi, all of you know, VT by ICQ times beta. RB is R1 parallel R2. Output resistance is nothing but RC. Voltage swing is determined by two considerations. One is by transistor going into saturation region. Avoiding that gives you this limit. And the other one is from harmonic distortion, which gives you the other limit here. And voltage swing will be the minimum of the two. And of course, all these quantities that you see depend on ICQ. And we have an expression for ICQ which relates it to the different resistor values and beta and VBE that you have here. And this is nothing but simple equation for the output loop here: VCC, VCEQ, ICQ, RC plus RT here. So we have a couple of equations that are there. And what you are given is all the things that, most of the things on the left-hand side. You're given AV, you're given RI, you're given R0, you're given V0M. So the left-hand side of all these equations are known to you, and you have to figure out what the appropriate values of RC and R1 and R2 and all of that are. But there are only basically, if you look at it, there are only 4 unknowns that are there here: R1, R2, RC, and RE. So 4 unknowns are there. VCC is given, is 12 volt, and since we have not given specifications for lower cutoff frequency and upper cutoff frequency, so you cannot determine CB, CE, and CC from lower cutoff frequency. What I would suggest is take some large value, 10 microfarad, for all of them. Okay, so our interest is not so much on lower cutoff frequencies here. So take each one of them as 10 microfarad. So that basically leaves you with 4 design variables: R1, R2, RC, and RE. Okay. Now, of course, what you can do is there is a popular design methodology among students that let me put some values here. As I said, let me put R1 10K, 20K, some value. Let's just throw, and you put in some value, and then you go ahead and simulate it. It's not going to match what you're looking for. Maybe if you're lucky, 1 or 2 specs may match. If it's not going to match, let me increase R1, let me decrease R2, and you iterate between guess and simulation, right? So you could do that, as I've been saying. This is a simple design where you can, with a couple of iterations between a guesses for R1, R2, RC, and simulation will help you come to a set of values for R1, R2, which will satisfy the specs. You can do that. But, our interest is not so much in the common emitter amplifier itself. Common emitter amplifier is important, but, I very much doubt that any of you are going to do anything with common emitter amplifier, maybe after you're done with 380. you did in E210 and 380, you're doing some common emitter amplifier. It's unlikely that in your life you'll ever do anything with common emitter amplifier. Okay, that's probably the end, okay, of common emitter amplifier. So common emitter amplifier by itself is not so important for us. What is important is what it teaches about design, about the design methodology. So you should carry that message more than the details of common emitter amplifier here. So in that sense, what we are using common emitter amplifier is a vehicle for teaching or for helping you learn how to do design in a more systematic manner. That's the goal. Rather than the common emitter amplifier, I could have taken a common source amplifier, I could have taken a differential pair, I could have taken many other circuit and done the similar thing. Okay, so it's a relatively simple example through which you can learn design. So what I would suggest is I'll point out how in a more systematic manner you should carry out design, which is that you have to determine R1, R2, RC, and RE. What you should do is from the equations and from the specifications that are given, you should try and determine what are the constraints on each one of them. What are the constraints on R1, R2, RC, and RE? After you generate all the constraints, then you go ahead and choose a value. You may still have to choose, but then you do after generating constraints on each one of them. And where do the constraints come from? From the specs. From the specs in the equation. So that's what I'll illustrate for you. For example, R naught equal to RC. We know this equation. And our specs is telling us that R naught should be less than 2K. Fine. So that will tell us that RC is, I'm not putting the value, RC is less than a certain value. Right? It has to be less than 2K. So anything less than 2K, you are fine with RC because you'll satisfy the specs here. If I look at this equation, AV minus ICQ RC parallel RL here, VT, what this tells us is, if RC is, if RC is more or less decided by this quantity here, what this will tell you is that to get gain above a certain value, forget about the minus sign here. If you want to get gain magnitude which is above a certain value, it would require ICQ to be larger than a certain value. Okay, so it would tell you that ICQ has to be larger than a certain value A2, whatever that A2 is. As long as you are larger than that value, your gain will be greater than 100. Okay, so you'll get a constraint on how small ICQ can be. Okay, so it will give you the lower limit on how small ICQ can be. If I look at Ri here, now you have to make Ri which is greater than a certain value. So this is going to tell you how large ICQ can be. You can't go ICQ above a certain limit because then you will not be able to satisfy the specs here. So if I look at these two, they will tell you that your ICQ has to lie between these values, an upper limit and a lower limit. Similarly, I've not shown here, if I look at the voltage swing here, the voltage swing, if you look at this limit is also telling you that it would also put a constraint on the lower value. If ICQ is below a certain value, you will not be able to get the sufficient swing here. So, sufficient swing here. This one will put a limit on how large or how small VCQ can be. So what you do is you use each one of these equations here and you generate constraints. Constraints on RC, constraints on ICQ, constraints on VCQ. If you do that, what you will end up, if you do that and analyze, we'll show you with an example in a minute. If you do that, at the end of it, what you will be able to get is a value of RC and ICQ. RC is obvious here, looking at from this particular one. One can get a value for RC. And by looking at all these things are generating constraints for ICQ. And therefore, after analyzing it, I can decide what would be an appropriate RC for my circuit and what would be an appropriate ICQ for my circuit. Now, once I do that, RC and ICQ, then I can go and look at these set of equations. For example, Ri is R pi parallel R beta. This is not the only way to do. Normally, one may choose RB much larger than R pi here, and therefore one would like to make RB, as I said, it would be much larger than Ri. It depends on your choice. RB some alpha 1 times Ri here. If I look at this current equation, we know that I want my design to be insensitive to beta. We'll come to that point a little later on. So ICQ, I want it to be insensitive to beta, and therefore I should make this term much smaller than RE. So it gives us another constraint that RE should be much, much larger than RB by beta here. And that again, it is your choice how large you want to make. So let's say your choice is alpha 2 times RB by beta here. If you put both of them together, then these basically decide your value of RE. So once you make this choice, how large you want to make RB as compared to the input resistance, how large you want to make RE as compared to RB by beta, and then immediately from there, then you get a value for RE. So you decide on RE, and remember we already know ICQ and RC. So then from ICQ and RE here, if you look at this expression, and RB also you would know. Once you made a choice, then RB is also known here, so you can determine R1 and R2. So then your design is complete. All that you had to do was determine R1, R2, RC, and RE, and that's what you will get at the end of this particular process. Okay, let me illustrate it here. Okay, so this is a summary of how you would go, summary of all the equations that are there, and how you would arrive at. Let me illustrate it for you. I'm going to assume a certain characteristics. I'm assuming a beta of 100. Beta may not be 100 for your transistor. As I said, you've already measured the characteristics of transistor, and you are sort of aware of what beta you're getting. Okay. So as I said, the first thing that we do is we choose a value of RC. So we get 2K. I've chosen it equal to R0. If you want, you can try RC, which is less than R0 also. That's a choice. Okay. And you can see what the implications will be. All right. So RC I've chosen as 2K. Then if I look at my gain, then the gain tells me that my ICQ must be greater than 2.6 milliamperes here. That gives me that constraint. When I look at input resistance tells me that my ICQ must be less than or equal to 5.2 milliamperes. Okay. So ICQ and input resistance, these are the values that I get here. When I look at maximum voltage swing, when I look at harmonic distortion with 5% specification, I find ICQ must be greater than or equal to 4 milliamperes. Okay, so that tells me I see another limit on that. If I combine all of those limits, we get ICQ lies between 4 milliamperes and 5.2 milliamperes. The other one is I need to keep my transistor away from saturation region, so which tells us that VCQ minus VSAT must be greater than 0.8. Assuming VSAT of 0.2, we get VCQ must be greater than or equal to 1 volt. Now again, you have a choice. Suppose I make VCQ, I have to give some margin, I have to keep it a little bit away from saturation. I don't want it to touch the saturation region, so let's say the choice is 1.5. Once we do that, once you choose VCEQ and you choose RC and you choose RE, it puts a constraint. On how large an ICQ is. So if you choose VCQ equal to 1.5, it tells you that your ICQ, which is VCC minus VCQ by RC plus RE, it must be less than or equal to 4.2 milliamperes here. Now, if we put them all together, what we find, the constraint on ICQ comes out to be that these are the limits on ICQ. Lower limit is 4 milliamperes, upper limit is 4.2. And at this point, when you look at these kinds of results, you should be worried. Why should you be worried? When you're looking at your specs and you're deriving the constraint, you're finding to satisfy all these specs, my ICQ should lie between these limits. Why should you be worried at this point? Well, choose 4.1. So I'm going to choose 4.1. Why should you immediately get worried? Practically, what do you mean? Why will you not get? One very important thing that we are missing from all of this is as I said, this design has been done for beta equal to 100. What if beta is 150 or happens to be 200? Okay, remember, you are not going to make one single amplifier. In general, you want to make lots of amplifiers and then you want all these amplifiers to work. Okay? Now, what if beta happens to be 150 or 200? If beta changes, there are going to be variations. Not only that, I'll show you in a minute. The RC that you take, 2K, and if you go into the lab and you take 100 2K resistors and you measure their values, what will you get? You precisely measure the values. You will not get 2K. In some, you may get 1.9K. Somewhere, you may get 2.1K. You know that there's a tolerance. And if you want to make a really cheap amplifier, you use a very low, low tolerance, a very high value of tolerance resistor, let's say 10%. So it may go to 2.2K or it may go to 1.8K. A lot of variation in RC, in RE, in R1, in R2. And then what will happen? All that will translate into variations in ICQ. And therefore, when you what this is telling you is that my design margin is very narrow. I have to, this is telling you, to satisfy the specs, I have to be in between these range. And so my margin of error is very, very small here. Okay, so anyway, let's take ICQ equal to 4.1 milliampere here. And with that, you can then go ahead and find out all the other values that are there here. So you can choose RE, RC, R1, and R2. At this point, when you do the design, of course, you're going to get numbers like 2.3 and 6.54 and things like that. And you know that in the lab, when you go into the lab, the resistor values usually lie in you get certain values of resistor. For example, you get, let's say, 10K, 12K, 15K, 18K, 22, 27, 33, 39, 47, 68, and all that, right? In between, you don't get values. Doesn't mean that you can't get. If you want 57K, you can always take 56K and connect 1K in series, right? But then your circuit becomes more complicated. You have to take two resistors and all that, okay? It's easier if you can get, instead of complicating your circuit, if you can use one of those standard resistor values, okay? So that will, again, cause drift in your design, right? So, for example, if I have R2 equal to 6.6 and R1 equal to 2.3, I'm not going to use these values. So what I will use is R1 equal to 22K, R2 is 6.8K, which I can simply go and pick in the lab, RE equal to 0.56K, RC 2.2K. I'll use these values. Now with these values, of course, my bias point and all of that will shift, and I'll get results which are a little different. You can already see that with those ideal values that I have, I was satisfying all the specs. My gain was 158, requirement was 100, input resistance was 0.56, which is fine, output resistance was okay, voltage swing was barely satisfying. But then these are with these ideal values. Then when I use these more realistic values, single value resistors, then it's fine. All of these are okay, except that I was very close to these specs, remember, and my design now no longer satisfies the 0.77 because I changed the values of R1, R2. That's what I was telling you, that my margin, in my design margin is very, very small. Small changes somewhere in the circuit, and you'll end up not getting the specs that you want here. Anyway, so with the specs that are given, you go ahead and design, and after you are done with the design, then of course you simulate your design, and you make your circuit and you simulate. These are the things that you should do in simulation. Check bias point first. In any amplifier, check the bias point by doing dynamic DC analysis in microcap, which will give you all the currents and all the voltages. So do that and check whether you're getting whatever you've designed for. Then what you do is you do AC simulation. AC is nothing but gives you small signal values. So with AC simulation, you can plot gain versus frequency, and you can see what is the mid-frequency gain here. You can also look at what is the input resistance, and you can check that out. So both gain and input resistance you can check through AC simulation. And then what you do is you do transient simulation, and with transient simulation, you apply an input, you get an output here, you again check your gain, you can check your swing here, 0.7 swing, and you can check the distortion also. The AC mode in microcap, for example, if you simulate for one cycle, then microcap allows you to do harmonic analysis of the waveform. And if you do harmonic analysis, you'll get the fundamental, the second harmonic, and the third harmonic and all. Okay? So from there, you can figure out that for a swing like this, am I below my 0.5% limit on harmonic distortion? So you can simulate and check whether things work fine or not. Okay? This is what is from the harmonic distortion. Anyway, so this is relatively simple in the sense that you can do the design very quickly, and you can breadboard it and you can measure. All right. Now this is where, as I said, a little bit of a complication comes, And the complications are that the design that you have to do it not just for these specifications. That's part one of the design. The second part of the design is you have to do it under these constraints. That's the second part. That the transistor is BC547 whose current gain may vary. Right? You can talk amongst yourselves. You can go and look at the data sheet for 547 and you'll find current gain may vary a lot. Okay? Current gain may maybe 100, maybe, I think I was looking at the lab reports of some of the students. I saw they were reporting current gain of 120. The one that I had, one of the TS measure, he was reporting 280. So remember, 120, 280, it seems that the beta values can vary a lot. Okay, so current gain may vary significantly. All the resistors, let's say, have a tolerance of 10%. You can use resistors with lesser tolerance also, but let's design it for 10% tolerance. Supply voltage may have plus minus 10% variation. Supply voltage is not going to be fixed, plus 12. It may have plus minus 10% variation. Temperature, you want your amplifier to work both in winter and summer. So it should work at 0 degree Celsius and also at 50 degrees Celsius, okay, in these limits here. Now, so what we want you to do is do this design. You want to satisfy these specs under these constraints also, okay. Now, this is where I did the design without looking at any of the variations as I showed you, and I said design margin is very narrow. So what would happen is, if you try to do this, you'll find you cannot satisfy the specs. You cannot under these variations, you will come up with the conclusion that these specs cannot be satisfied. I cannot guarantee these specs. If you tell me that the resistors are going to vary as 10%, supply voltage will vary, temperature will vary, current gain will vary, then I cannot guarantee those specs. All right? You cannot guarantee those specs. Then my question to you is, yes, fine, you cannot guarantee these specs. What is the new set of specs that you can guarantee under these variations? What is it that you can guarantee? Okay, under these constraints. So you come up with now a set of specs that you can guarantee and do a design of an amplifier again. Another design. So two designs are there. First one, you forget about all these variations and all of that. You do a nominal design. Fine. And it may happen that when you breadboard in the lab, you satisfy all the specs. It may happen. But what I want you to do is design an amplifier which will also work under these variations. And with that, as I'm telling you, you cannot satisfy these specs. And therefore, I'm asking you to come up with a new set of specs. So it's like, you know, a customer comes to you and says, I want 1,000 common emitter amplifiers. He gives you an order for 1,000 common emitter amplifiers, and he says all of them should have these constraints, should satisfy these specs, right? Now, you're not going to take every transistor and measure its beta. You're not going to take every resistor and precisely measure it. You want to have one design, one R1, R2, RC, RE, such that with those values you can get the specs that you want. Now, it's your job then to analyze and tell the customer, look, I cannot do that. I cannot give you these kinds of specs. And then the next question that he will ask is, okay, what is the best that you can do? You can't give me gain of 100, or you can't give me input resistance of 0.5K. What is the next best thing that you can do? And that's what you have to determine. So I don't want you, of course, you can immediately slash gain by half, slash R in by half, and you say, here, these will work, which is very trivial. But that's not the point. The point is, what is the best, what are the specs which are closest to this that you can guarantee under these variations? That is where the challenge is. And here you will find somebody, there will be variations. Somebody will say, well, I'm not going to compromise on gain. Somebody may take that stand. I've left that freedom completely up to you. Somebody may say, I'll not compromise with gain. I'll maybe compromise on input resistance. You know, if you can't guarantee, so I'll compromise on input resistance. Maybe I'll compromise on HD, harmonic distortion. Somebody else may compromise on gain and not on something else. All right. So unless you copy from each other, we are going to have different designs, because different people should take different stands. Somebody should say, I'll compromise on gain. Somebody, compromise on something else. Okay. So this is what we want you to do. This is something which is more challenging. That under these variations, I want to come up with a set of specs and a design which will work. Okay. Now, let me illustrate to you in the remaining time that I have, what are the impact of variations. Okay. So here is a design, a nominal design. Let's say you have come up with a design 22K, 6.8K, 0.56 and all. Fine. Right. Now, remember, if you go to the lab and each one of those resistors are going to have a tolerance. Okay. So let me just show you what the effect of tolerance will be. Okay. So there's a way of doing this is, for example, what one does is a kind of a simulation called Monte Carlo simulation, where, I mean, it's a fancy name, but what I'm doing is the following. Given a value of R1, R2, RC, and RE, I can, using a formula, calculate what is ICQ, right? Given all the values, RC, R1, R2, beta, I can calculate ICQ. But now what I do is, I make RC a random number. Its nominal value is 2.2K. I make RC a Gaussian random variable. MATLAB and all that will allow you to do a Gaussian random variable. So what I get is, I get 1,000 values of RC, 1,000 values of RC, and where is it? I don't have, yeah, here. So this is what I do. I take 1,000 values of RC here, and I've plotted it out. Each one of them is random. It has a certain standard deviation, which is an indication of the tolerance. And you can see how RC will actually vary here. So this is what would happen in real life. If you take 1,000 2K resistors, you will find these values will lie. And typically they will lie on a bell curve like this here. With a mean value which is 2.2K, will have a certain standard deviation. You will get some resistors which are as large as 2.4K, some resistors which are as low as 2K. So now my RC is going to lie like this here. I've taken 1,000 values of RC. And how they have been generated? Through a Gaussian random variable with a certain mean and certain standard deviation. Okay. Now with these RC values, what I do is, now each one of those resistors are going to be like the same. R1 is also going to be a Gaussian random variable with a mean value of 22K and with the standard deviation which is 10%. 3 sigma, let's say, is 10% tolerance. And similarly, R2 and RE, all of them are like that. Okay. Take 3 sigma as 10% of the value. Okay. So all of them are random variables now. So R1, R2, RC, and RE are all random variables. Now what will happen to ICQ now that I calculate? That will also be a random variable. Okay. So let me show you what ICQ happens to ICQ. Look at the value of ICQ. Nominal value of ICQ is 3.48. But because of just the tolerance, 10% tolerance, it can go as high as, you can see here, all the variations in ICQ that are there here. 3.4, 3.6, 3.84, and all of that. ICQ is also varying. Okay. The variation in ICQ is 16.4%. I had 10% variation in all the resistors, and the ICQ varies at 16.4%. Now, because of variation in ICQ and all the resistors, all my specs are going to vary. So let me show you what happens to the gain. If I evaluate the gain is varying like this here. With a maximum value of 183, minimum value of 119.5, so which is fine. Because my specs were what? 100. So even despite all the variations, I'm above the limit of 100. So my gain will always be satisfied here. So I look at gain, how gain varies for under all these variations here. Now, mind you, I've only changed the resistor values now. R1, R2, RC, RE. Besides that, beta also changes, temperature also changes, a lot of other things will change, okay? So, I'm showing you input resistance, in how input resistance varies. Here also maximum is 0.7K, minimum is 0.55. I'm fine with input resistance also. Next, I look at voltage swing. There are two limits on voltage swing. I look at these two limits here, VCQ minus VC sat and the harmonic distortion. If I look at the first limit here, I find it can go as high, mean value is 2.18, maximum is 4 and minimum is minus 0.25. Which means what? VCQ minus VC sat. Under variation, some of my designs will enter into saturation region. They are going to enter into saturation region. Okay, which means that my amplifier will fail completely. In fact, the previous result was not very accurate because this AV has just been calculated from a formula, ICQ RC parallel RL. It assumed forward active mode. But now you are seeing from here that under certain cases, my transistor is entering into saturation region, which means that I will not get any gain. Okay. The other limit, VOM2, you can see here what is happening. Mean value is 0.76. This harmonic distortion is is going as low as 0.62. Okay. Now the trouble is, as I said, I've only taken R1, R2, RC, and RE. Beta is also a random variable. Okay. So beta may, in this case, I've just taken beta with a nominal value of 100 and with a standard deviation of around 25, sigma of 25. So beta is also going to vary like this. So let me add beta variation also. On top of that, I'm going to now evaluate my design at 50 degrees Celsius and with the supply voltage of 13.2. Supply voltage, remember, could go could have 10% plus minus variation here. So I'm evaluating it at 13.2 and temperature of 50 degrees Celsius. Now temperature has several effects. Temperature can change the values of each one of those resistors, R1, R2, RC, RE. I've not taken that into account. Temperature can change beta. Okay, I've not taken that into account. The only change effect of temperature that I've taken is the base emitter voltage, which you assume it to be 0.7. That decreases with increase in temperature, roughly at the rate of 2 millivolt per degree Celsius. So that's the only temperature effect that I've taken into account. There are other temperature effects also, which have not been taken into account. So 50 degrees Celsius, which means the base emitter voltage is no longer 0.7, but is smaller by a certain amount. You can see how ICQ varies. The gain and all that is given here, Rn is given here. After analysis, what we find is, if I make 1000 amplifiers, 56 of them have a voltage swing which is less than 0.72, which means that 56 out of 1000 will fail under those constraints. 56 out of 1000. Now, which is, maybe it's okay. You make 1000 amplifiers, you measure their characteristics, and 56 of them you reject. You say you reject, and the remaining 9,000 something, you send it out. You could do that. All right. The next thing is you have to evaluate at other extremes also. 0 degrees Celsius, a lower supply voltage here, 10.8, and so one is evaluating under that constraint. And in this case, now look at that. 0 degrees Celsius, supply voltage of 10.8, 944 amplifiers have VOM less than 0.72. Your design just goes. It's a horrible design. You're not able to, 944 fail under that constraint. Where each one of those resistors have a tolerance, plus temperature is 0, so in winter is going to fail your design. Winter, and when the power supply is not very stable, lower, 10.8, then almost all your amplifiers are failing. All right, so which means that the design that I have is not going to work. Under, my design has to be guaranteed under all these variations is not going to work. If 944 of them are going to fail, which is basically telling us that I cannot guarantee those specs under these conditions. Okay, so now how do you do the design with these variations in mind? Obviously, you can't go and choose a certain values, run these Monte Carlo simulations, see what is happening, then tune and run and back and forth. You don't do that. What you do is, you do a worst case design. You come up with a worst case scenario and you see that your design works under those worst case conditions. If it works under those worst case conditions, it will always work. Okay, so that's one way of approaching it. So for example, I would do now the design under worst case scenario. So if I look at voltage gain, all the variations that can take place here. When is the voltage gain worst? When when RC is minimum. I know that my RC is going to have a tolerance. So I'm going to take the lower value of RC. RL is fixed, so I'm not going to bother. So when RC is minimum, when temperature is maximum, because temperature enters here, temperature is maximum, and when my ICQ is minimum. That's the worst case scenario for voltage gain, because each one of those quantities now you know that is a random variable. So when RC is minimum, temperature is maximum, and ICQ is minimum. The next thing I ask is, when is my ICQ minimum? So when I look at this ICQ minimum, I find when my R2, you can look at it when my R2 is minimum and R1 is maximum. Okay? When my RE is maximum, normally, and when my beta is minimum. So you can come up with those set of criteria. VCC is minimum, and temperature, this says temperature should also be minimum. Because why? When you make temperature small, VBE, this term becomes high and ICQ becomes low. But now you're getting a conflicting, this says the worst case scenario will occur at minimum temperature, this says maximum temperature. If you look at it, temperature directly enters here in the denominator, while temperature is a smaller term here along with this particular term here. So the effect of temperature on this term is much smaller as compared to this one. So the worst case scenario for voltage gain then is RC minimum, ICQ, temperature maximum, R2 minimum, R1 max, RE max, beta min. So you take this worst case situation here. And for each one of those variables, you know what is the minimum value. You know the tolerance levels. You can have an idea of what is minimum beta, what is maximum beta. And now what you have to do is make sure that under worst case scenario, your voltage gain satisfies these specs. Same way, you can go ahead and look at input resistance. What is the worst case scenario for input resistance here? Right, so by looking at these equations, you can come up with the worst case scenario for input resistance as well. And like that, you go and look at the voltage swing. What are the worst case scenarios? So after you do that, then what you do is you do the worst case design. Now you will say RC minimum parallel RL VT max into ICQ minimum should be greater than or equal to AV. That is the equation that I should now look at. Okay, not a simple earlier equation. That similarly, worst case scenarios have been put. VT minimum, ICQ max, beta minimum must be greater than RL. So with all these worst case scenarios have been put in, and the equations that we had have been rewritten, keeping in mind these values that are there. Now what you have to do is, you have to now, is slightly complicated. You have to come up earlier, you were given the right hand side or left hand side and you had to obtain RC. Now you don't have either one of them. You have to come up with the right hand side also AV, and you have to RN and VOM and all that, and you have to come up with a set of values for RC, RE and all of that, such that under worst case scenario that you have here, your design will work. Okay, and you have to come up with that. All right, so this is the part that will require a little bit of iterations and working out. Okay, and as I said, in MATLAB and all that, you have the option of, you can very easily generate a random variable with a certain mean value and a certain standard deviation. So you can run your simulation, you can run your simple MATLAB program, and it can tell you, you can get these plots, histograms, how your gain will vary and how your input resistance will vary and output, all of those quantities here. And at the end, you can check out that design that you've done under this constraint, how much failure rate it will have, how many, if you have 1,000 such designs, how many of them will satisfy these specs. Okay. Last, when you come to the lab, as I said, you will have two designs. One design is where you forget about all the variations and you just do a simple design. So you come to the lab, all of you are going to have, because we have a standard specs, all of you will have the same design. Just go ahead and come to the lab, measure the breadboard it, measure bias voltage at each node. That's the starting point of all measurements. Measure the bias voltage. Okay. Next thing is measure small signal voltage gain and input resistance in mid-frequency range here. You have to make sure that you're in the mid-band range. Mid-band range, the way you make sure is that as you increase the frequency or decrease the frequency, the gain is not changing. Okay, gain is not changing. The other way of making sure is that if you look at between here and here, the output, you'll get 180-degree phase shift. If you're not in the mid-band, then the phase shift between input and output is not going to be 180. Okay, so that's the other way of ensuring. So make sure that you're measuring in the mid-frequency range. Use the small signal voltage here as small as possible. And still you're able to measure it, okay? Because then only you're under the small signal regime here. Measure voltage swing and associated distortion. So what you do is you apply a very low value, measure the output voltage here, and your oscilloscopes also have a FFT, so you can get the spectrum of your sinusoid here. Otherwise, I'll just show you what you should notice. If your sinusoid is distorted, one of the effects of distortion is that the positive peak will be different from the negative peak. Okay, and therefore a measure of distortion can be obtained very quickly by measuring what is the positive peak and what is the negative peak, and just using adding up and all that you can show easily. Okay, you can look at the slide, and from there you can get an estimate for harmonic distortion. If I think we have a variety of oscilloscopes in the lab. If your particular oscilloscope doesn't have FFT, in case, then what all that you do is, when you measure the waveform, measure the positive peak and the negative peak. And from there, you can estimate how much harmonic distortion is there. Okay. And so what you do is, you start with some input voltage here, small input voltage, measure the output voltage, positive peak and negative peak. You can quickly calculate what is the harmonic distortion. Keep on increasing the voltage here. The output voltage will keep on increasing, and you can see how the distortion is increasing. All right. And so take a voltage swing versus distortion characteristics. And then you can find out where is 5%, where is 7% and all. Although this is not required, it's not a part of specs, but I would like you to measure the frequency response also. What is the lower cutoff frequency and what is the upper cutoff frequency of this particular amplifier here. So come to the lab prepared with your values, R1, R2, RC, RE, nominal design, just put it there, breadboard, and measure these things there. Right? So that's the first part. Second part is a different design where you will guarantee that these specs, no matter what the variations are, this particular design will always work. Okay, so bring that design, put in those values, R1, R2, RC, RE, and check out what you get. Okay, so in the lab, there should not be any surprises. This is a straightforward common emitter simple amplifier with R1, R2, RC, RE. It should work. Okay, so there's no problem. The interesting things are more not so much in the lab, but before the lab, doing the design, finding a set of specs that you can guarantee. So that's much more interesting. Coming to the lab, it should be trivial. Okay. All right. So